Hey everyone, so let's dive into a topic that seems kind of complex, but is actually happening all around us all the time. I'm talking about everything from your morning coffee cooling down to how a car engine works. We're going to crack the code of what we call transient heat conduction. Seriously, have you ever thought about this? Why does a big baked potato stay dangerously hot on the inside forever, but a little steel bolt you drop cools off in just a few minutes? It's a great question. And it all boils down to a really cool engineering principle we're going to break down today.
Okay, so first things first. Let's build on some of that intuition you already have. We all kind of know why coffee gets cold or a potato stays hot, right? Let's put some science to it.
So think about it like this. Heat trying to escape an object is on a two-part journey. The first part is the traffic jam inside the object. How fast can the heat even make its way to the surface? That's what we call conduction. The second part is the open road outside the object. Once the heat gets to the surface, how fast can it get whisked away? That's convection. So for any cooling problem, the real question is, where's the bottleneck? Is it the internal traffic jam or the external open road?
Now, this brings us to a super useful tool engineers came up with. It's a simple rule that lets us measure exactly where that bottleneck is.
It's called the Biot number. And hey, don't let the name scare you. All it is a simple ratio. It's the internal resistance, our traffic jam, divided by the external resistance, our open road. It just tells us which one is bigger and by how much. Simple as that.
And here it is. This is the magic number, less than 0.1. If the Biot number is smaller than this, it unlocks a much simpler way to solve the problem. It tells us something really crucial.
You see, when the Biot number is that small, it means that internal traffic jam we talked about, well, it barely exists. Heat zips to the surface so fast that the entire object basically has the same temperature everywhere as it cools down. So the real bottleneck, the slow part, is all on the outside. And when that's the case, we get to use a much easier method called the lumped system analysis. All right, so theory is one thing, but let's actually see how this rule works in a real-world problem. You know, the kind of thing you might see in a textbook or on an exam. So here's the setup. We're doing something called quench hardening. We take a super hot steel rod. We're talking 850 degrees Celsius, and we dunk it into a water bath to cool it down to 95 degrees. Our job is to figure out two things. First, how long does that take? And second, how much total heat actually moved from the rod to the water? And here's what that looks like in a diagram. You've got the hot rod in the 40-degree water. See that little H on the side? That's the convection coefficient. It's basically a number that tells us how good the water is at grabbing heat and carrying it away. That's our open road.
So before we dive into the numbers, here's our game plan. It's a simple three-step process. First, we have to calculate something called the characteristic length. It's just a way to represent the geometry of the object. Step 2, we use that length to find our all-important Biot number. And then, for step 3, we check our magic rule. If it's less than 0.1, we get to use the simple formula to find the time.
Okay, I know this looks like a wall of math, but don't worry. Let's just focus on the important part. Look at the second block of calculations for the Biot number. You see the answer there? It's 0.088. And hey, that is less than 0.1. So, ding, 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 our simple approach is totally valid. That lets us use the lumped system formula at the bottom, and if you follow that all the way through, you get our answer, 254 seconds.
Now, for part 2 of the question, how much heat was transferred? Using this formula here, which basically just multiplies the mass, the specific heat, and the temperature change, we find that a whopping 10.1 megajoules of energy got dumped from that one little rod into the water. That's a lot of energy.
So why do we actually care about any of this? I mean, calculating cooling times for steel rods, does this stuff matter outside of a classroom?
Oh, you better believe it does.
Here's the thing. That whole calculation we just did is at the heart of quench hardening. And that process is what gives us the incredibly strong, durable steel parts that we trust with our lives in high-stress situations. We're talking about things like critical parts in your car's engine or even the landing gear of an airplane. Getting that cooling time exactly right is what makes them safe and reliable. It's not just homework, it's a huge deal.
Okay, let's switch gears and do a couple of quick thought experiments. This will help make sure the idea has really clicked.
So just think about it for a second. We've got two things in an oven, a really thin aluminum cookie sheet and a big, thick ceramic brick. Which one is going to have a lower Biot number? Well, which one has the bigger internal traffic jam? It's the brick, right? Heat has a long, slow journey through that thick ceramic. The thin aluminum conducts heat super fast, so its internal resistance is tiny. That means the cookie sheet will have a way lower Biot number.
This is a fantastic design question. Okay, so we want to cool our steel rod down even faster. What's the better move? Should we use a different fluid that's way better at pulling heat away, meaning a higher H value? Or should we make the rod out of some super material that conducts heat better, a higher K value? Well, remember, for our rod, the bottleneck was on the outside. So if we want to speed things up, we have to clear that open road. Using a fluid with a higher H will make a huge difference. Improving the K wouldn't do much because the internal traffic jam wasn't the problem to begin with.
Okay, to wrap things up, let's put together a little toolkit for you. Just a few things to keep in your back pocket to help you nail this topic on your next exam.
Here's a quick cheat sheet of all the main players in the formula. Now really pay attention to H and K. Remember, H is all about the fluid on the outside. That's our open road. And K is all about the material of the object itself. That's our traffic jam. Knowing the difference is absolutely key. This is probably a good slide to screenshot for your notes later.
And finally, here are 4 pro tips to help you avoid the most common mistakes I see students make. First, and I cannot say this enough, always calculate the buyout number first. It's the gatekeeper. It tells you which path to take. Number 2, watch your units. It's so easy to make a small mistake there. 3, know that the formula for characteristic length changes for different shapes. And 4, always remember to write down why you're allowed to use the simple method. Justify your assumption with the buyout number.
So look, what you've learned today isn't just an equation for an exam. It's a whole new way of looking at the world. So next time you're waiting for a slice of pizza to cool down, you can think about its buyout number. Is the bottleneck the thick crust, or is it just the air in the room? Keep asking those kinds of questions. Thanks so much for tuning in.